Control it. Welcome to Morpheus Chair, the program where you learn how to build robots like these from your comfy chairs. So this will be a big episode that will be divided into 3 because we're going to create a program that makes this bad boy follow a line on the floor with the camera. So to do this, we need to do 3 main things. The first one is have a control program that moves the wheels in the best way possible. The way we can do that is with a differential drive. So we can control the speed of the wheels as best as we can with the hardware that we have. The second part will be to create a script that with the camera you can detect a line and generate a path to follow. And the third part will be to design and 3D print a stand for this camera so that we don't have this dodgy way of having like this, the camera. So we are going to design it in an online free CAD software. Okay, so let's go to the first part, which is let's build a differential drive for this bad boy. So, to the workbench, to the workbench, to the workbench, to the workbench. What did you say? To the workbench. So here we are in a simulation of our beloved robot. I've launched it using ROS Development Studio, which is an online ROS development platform, totally free. I've left the link of the ROSject in the video description, so you can click it and you'll have the ROSject ready to go. So to launch this, just launch Morpheus Chair, launch in the Turkey Town Gazebo, and you'll get a simulation like this, which is a modified version. So what are we going to do? So what we are going to do is I'm going to open the IDE. You can do this on your local computer. It's exactly the same. It's just more convenient to show it like this. And in the Git of MorpheusChair, I've uploaded the latest version of the motor driver. So what we have to do in this first episode of this 3-part series is create a new motor driver that has differential drive implemented. Okay? So as you can see, I've changed quite a lot of the code, and we're going to talk about it right now. So remember that we are using move with command vel. So this is the script that is launched in order to move it through the keyboard. And what we have here is here we have changed everything so that we just use this set command vel, and we give it the linear speed given by the command vel captured, and the linear speed and the angular speed. And with that, the motor driver does whatever it has to do to implement this differential drive and move the robot the way it should be moved. Okay, so this is much simpler than the last episode that we did this, but this part is much more complex. So if we go to this set command vel method, you can see that it's not that difficult. So what it does is the following. So the first thing is we are going to calculate the body turn radius. So based on the linear speed and the angular speed, what's the radius, the turn radius of this robot? So what we are trying to do is generate a kind of circle here, and depending on the linear speed and the angular speed, the circle will be smaller or bigger. It will have a bigger radius or a smaller radius. If it has a smaller radius, then it means that it turns more than it goes forward or backwards. Bigger radius means it goes more forwards or backwards than turning. And the extreme would be from one side pivot, and from the other side would be going forwards and backwards. So forwards and backwards would be the extremes of the infinite radius circle. Pivoting would be having a circle just in the center of the body. And then in between we have moving forwards with some turn of some kind. We are calculating based on this linear and angular speed this body turn radius. And based on that, then we have to calculate the turning radius of the left and right wheel. Why? Well, because if we go to the simulation again, we can see that if the robot turns left or right, if it turns right, then if it turns right, it means that this right wheel will have to turn less than this left wheel in order to make this turn. Okay, so that's the main objective of the differential drive. So we have to calculate the turning radius of each of the wheels, and based on that, it will also calculate the turning speed. Yeah, because again, if we're turning right, for example, this wheel will generate a smaller radius circle than the outer wheel, the left wheel, which will generate a bigger circle. Yeah, so we calculate then based on the body turn radius and the angular speed, and based on if it's the left or the right wheel, we calculate what we have to do. So we have the turning radius of both wheels, then we calculate the RPN, which is the speed at which the wheels turn. Once we have that, then we can set the movement. So now we execute the movement. We move the right wheel at certain speed and the left wheel at certain speed. Yeah. So let's have a look how we calculate this body radius. So we calculate this body radius with this very simple formula, which has a singularity, which a special case, which is when angular speed is equal to 0. Why? Because body radius is linear speed divided by the angular speed, but if angular speed is 0, then we have a body turn radius infinite, which makes mathematical sense because angular speed of 0 means that it's going forward. So we have an infinite radius circle. Yeah. So it makes sense, but in practical sense, we can't use infinite values for turning radius. So basically what we do is we set none. Yeah, that was a fairly easy calculation. So next step is, okay, we calculate the wheel turn radius. So we give it the body turn radius that we just calculated, the angular speed, and the wheel. Which wheel is it? Because depending on which one, it has the formula changes. We get the body turn radius and then we multiply it by the if it's left or right wheel, and then this is basically the wheel distance. So the distance between the left and the right wheel, and we divide it by 2. And this is what we add or subtract from the turn radius, okay? And depending on the body turn radius, could be positive or negative, depending on if it's going forwards or backwards, but this will adapt. So we can get negative radius, which is when we're going backwards, and then this will change, obviously, because here, the left, if we go forward, we are subtracting, but if we go backwards, it's adding, really, to a negative value. Yeah, okay. If we don't have any turn radius, then the wheel turn radius is none. Why? Because we're going forwards or backwards. Once we have calculated this, I leave in the video description more pages and resources to understand better these formulas, but basically this is a fast way of doing it. So once we have calculated this, then we calculate the RPMs, which is the turning speed of the wheels, which depends on the wheel, the radius. So if we go here, we have the wheel turn radius, and then the linear speed and the angular speed of the base. I have a small explanation of how to calculate this, but essentially what we're going to do is, if the turn radius is not none, so we are turning, then it's the wheel RPM is the angular speed multiplied by the wheel turn radius, and this is divided by the wheel radius. If we're going forwards or backwards, then it's the linear speed divided by the wheel radius. The only difference is that you can see that here we are calculating our own linear speed of each wheel. But if we're going forwards or backwards, then both are the same as the base. So the speed of the wheels will be exactly the same. Bear with me here. So once we have this, then we just have to set these speeds, and we have to move the robot, the physical robot. So here, what we're going to do is we set, and depending on which values, so if they are positive, negative, if they are 0, all the combinations, we have them here, because here we have to set the pins, we have to set the motor driver configurations in a way that it moves accordingly. Yeah, because as you can see, you don't give negative values of speeds, you just give positive values, and depending on if they are positive or negative, then we set a configuration. So for example, let's say the easiest one, which is, hey, the wheel speeds are positive both, which means I want to go forwards. So I want to go forwards, like that, or less. We'll talk about this phenomena here, but essentially we're giving this here, and there's a multipliers, which is related to how we set this. So if we set the speed, you can see that we're setting both different ways, but it's exactly the same. And what we're doing here is setting the PWM, and it's proportional to this multipliers and the base PWM. Basically, it's a way of changing the speed through PWMs. That's why we use multiplier, and depending on if we pivot or not, we will change that pivot. It's basically a way of making it behave as it should, as far as we can do it. So here we are setting the PWM. That's the only thing that's important. So once we have set this, then we set the direction. So in this case, forward, it's here, and what we are setting is the motor 1 in this polarity and motor 2 in this polarity. And that way it will go forwards. And the mechanism is exactly the same for all the other cases, just that if it's, for example, if the right wheel is positive, which it's going forwards, and the left is 0, means that we want to turn left. If it's positive, the right wheel, and negative, the left wheel, then we have to pivot. And it's more or less the same thing over and over again. And the magic is done by the differential drive formulas, because that way it calculates the speed and the direction of turn of each of the wheels based on the dimensions of the robot. Like the base, the wheel separation, and the wheel radius, based on all that. So it's quite intelligent, actually, the differential drive. And that's it. So we do that for each of the cases that we have. So basically positive, negative, and 0. For example, here, both are 0 means that it stops. So we set the speed, which will be 0, and then we stop. If you did it everything more or less like this, you should have a behavior, something like this in the real robot. So here we have a simulation to see more or less what it would happen. It's using a differential drive, a simulated differential drive, so not the one that we've implemented. But as you can see, if we pivot, both wheels move at the same speed, but in different directions. If we go forwards, you see that it has this strange behavior. This is because one wheel goes faster than the other. So one goes before the other, so it has this starting behavior. And we'll have more or less the same behavior in the robot, so you will see just now. But it's a good way of practicing your code just using simulation. And we'll use this a lot for the line following, because we will be able to do a lot of tests, simulated tests, without using the real robot and spending battery, time, and energy in that. Yeah. Okay, great. So let's go to the real robot. So now what we're going to do is connect through SSH and launch the minimal systems to make the robot operational and move the real robot. So I'm going to put this here, and we're going to connect. And we're going to go to the Catkin workspace source, and we're going to launch Morpheus. And I think we don't need any cameras for now, only the motor driver start. So let's start this. So we don't need the robot bring up with the camera also. There we go. Okay. And here we're going to launch. So again, Catkin workspace source. And ROS launch Morpheus. And then we're going to launch the keyboard teleop in order to move the robot through the script that we talked about. And that's it. Now we can move the robot around. So if we give it power, we move the keys around. Let's test it on the floor. Okay, so we're ready to move it. So let's move it forwards, backwards, pivot right, pivot left. Let's pivot again. Now let's try to move forwards right. Not good. Then forwards left. There you go. And backwards the same way. So what we can see here is that it works forwards, backwards, left, and pivot right. So there's no problem there. The problem comes when we want to do the differential drive. And the reason why is because differential drive needs a very good control in the speed of the wheels. If the wheels don't go at the speed that they should, it doesn't work. So how could we do that here? Well, in this case, the best strategy is not using differential drive in what's the forwards left and forwards right turning. So we can turn pivot. It works perfectly. Actually, it works really well. And forwards and backwards, it's more or less, but you can see that it happens the same in the simulation. It has a tendency to turn to the left, and that's because if we get the robot, so let me try to move the robot. There we go. I'm going to go forwards, backwards, pivot, pivot left, pivot right. Have you spotted something? So there's one wheel that's slower than the other one, and that means that it never goes forward at start. So, and not only that, but it seems that there's a wheel that it doesn't have that much torque. So that could be solved just by adjusting the speed and the power that it's given to each of the wheels. But for the moment, it's more or less acceptable. We can turn and we can go forwards and backwards more or less. And for now, it's more than enough. We're back. So it's all for today. Thanks a lot for watching the video. Hit that like button if you liked it, and see you in the next video. Until then, keep building, keep building, keep building. Check one. Welcome to projections. Projections, no.